Terrible? Terrible? That's okay. Midterms are the hardest. At least that's what I've always found. Do you guys agree midterms are worse than finals? It's just too much to balance studying, classes, labs, assignments, and then studying for midterms. It's too much. Finals are, at least in my opinion, much easier. At least I think most of you guys probably feel the same way. But you guys should be almost done your midterms now. should be. Just getting started. So most of your classes must have 2 midterms then. No? And you're still doing them the whole time? Oh, wow. That's, spread them out, yeah. This class is the only one, I think. Is this class the only one with 2? No. I'm seeing some yes, some no. I guess that's the fun of having 3rd and 4th year students in here. My advice, your last year, your graduating year, so if you're co-op 5th year, traditional 4th year, it's the easiest. So hang in there, you guys are almost at the finish line. I mean almost. 4th year, you walk in, you go, oh, this is nice, you go home and sleep, and that's basically 4th year. 4th year, or I guess 5th year, it's easy. So hang in there, you guys are almost at the end. All right? Almost. So before we begin, I just wanted to say thank you guys. I was looking back on this course, and we're at lecture 12. There's 20 lectures that we're actually testing on. Right, lecture 12. We're at assignment 6, means there's only 4 more assignments left, so like it's coming to an end. And you guys have been amazing. I've talked to other instructors, especially the other 8 a.m. instructors, and they said, my attendance is next to nothing. And yes, this class, the attendance has gone down a little bit, but for the most part, you guys are here. You guys are awake, which is a lot to ask for. I know when I took 8 a.m. classes, I would either not show up or show up and sleep. So the fact that you guys are awake and here, it's amazing. So I just want to thank you guys for making my life so much easier. There was a lot of stress with the professors about this hybrid delivery system, but you guys have made my lives, just one life. You guys have made it very easy. So I just want to thank you guys for that. All right. So yeah, today we're going to be talking about constitutive laws. Now, constitutive laws is bittersweet. It's bittersweet. It's good news and bad news. You guys want the good news? It's very easy. It's always just one calculation. And that calculation will be done through Mathematica. So in terms of computing something, easy. You guys are going to laugh. It's very easy. It's bittersweet. And the bad news is that the actual calculation, it can be kind of tedious. It's like the von Mises stress. You guys remember von Mises stress? Big, long square root equation, real pain in the ass to type in Mathematica. It's going to be the same thing here, where the matrix that relates stresses to strains, that's the whole goal today. How do we relate stresses to strains or vice versa? The matrix, very simple, but it sucks to type out because it's going to be 6 by 6. All right, 6 by 6. It's not very nice. So here's my kind of only tip today. When you guys do this matrix in Mathematica, save it. Put it somewhere so for future assignments, you guys can always just copy and paste. Because the stuff that we're going to learn today is going to apply heavily to the last part of the course. I talked about it with the students in the first seminar. It's actually very, very nice what we're doing. What it's going to turn out is a typical problem in reality is going to be like this. We're going to have position functions. Position functions. With these position functions, we can find displacement functions. This is what we talked about in strain. From displacement functions, we can find our strain tensor. And then now today, we're going to take our strain tensor and we're going to find our stress tensor. So basically, we go from displacement functions all the way to stress. It's very beautiful what we're doing. And this is the topic of midterm 2. What are we going to do in the last half of the course is look at those displacement functions. Every problem you guys have seen in strain, and as you guys will see this week, I just give you the displacement functions. I say, here's a plate, and here are the displacement functions. What we're going to do in the last half of the course, or I guess the last third of the course, is we're going to try and talk about, okay, how do I get those displacement functions? So that's the whole goal. And by the end of this course, If I give you guys a beam with, let's say, a distributed load, a concentrated load, it's fixed at both ends, whatever, by the end of this course, you guys are going to take that beam, which is loaded, you're going to find its displacement functions, then you can find its strain, and then you can find its stress. That's the whole goal of this course. Taking something that's loaded, as any structure would be, and finding the stress and strain in that structure. That's the whole goal of this course. As we're going to see today, we're covering kind of the last part, which is if I have strain, how do I find stress? Or vice versa. Because again, when we looked at stress, I always said, here's the Cauchy stress tensor. Here you go. But I didn't really describe how we get it. Well, typically we get it through strain. How do we get strain? Well, we get that through displacement. How do we get displacement? Well, that's what we're going to talk about at the last half of this course. As we can see, everything is very nicely intertwined with each other, and it's a very nice procedure. That simulation software that I talk about, it does the exact same thing as I just described. Every simulation software you guys use, although you may not know it, it finds displacements. From displacements, it finds strain, and then from strain, it finds stresses. And the methods that we're teaching you guys here, same methods in the software. But you're saying, Clayton, linear, nonlinear? Yeah, but it's just a little modification. It's the exact same method as in the software. The only time the software starts to differentiate from where we do is finding those displacements. As we're going to see, everything can be modeled with a differential equation. And that's what we're going to do. We're going to take a differential equation. We're going to solve it to find our displacements. Now, in reality, let's say I have a concrete beam. Concrete cracks. Do you think it's easy to solve a differential equation that isn't smooth? Because if concrete cracks, it's not going to be a smooth function. So is it easy to solve one of those differential equations? What do you think? I'm seeing a lot of no's. Exactly. So that's where the simulation software starts to differentiate, is we use approximation methods to approximate the differential equations. In this course, we're going to deal with nice differential equations so we can solve it. But in actuality, if this was the grad course, you guys have learned everything in the graduate course. The only thing that's going to differ are how we obtain those displacement functions. Everything we're learning today, this comes directly from the grad course. You guys are now experts. Well, at least after this lecture. So let's see if we can scare you off. Today, constitutive laws. Basically, if I know my strain, can I find my stress? Or vice versa. If I know my stress, can I find my strain? That's the whole goal of today. So let's take a peek. So constitutive laws are stress-strain relationships. If we know a stress tensor and a strain tensor, can we determine a relationship between the two? As I've already hinted, yes. This would be a very short PowerPoint if the answer was no. I would just say no, and that'd be the end of the lecture. But of course we can. But this is going to be a very unique scenario. At the beginning of this course, I said that I have two words that I'm going to use interchangeably: matrice and tensor. I said for our purposes, all of our tensors are second order, so we can treat them as matrices and vice versa. This is where it's going to start to differentiate a little bit. All right, so keep that in mind. So let's say that I have a stress tensor and I have a strain tensor, and I'm looking for the relationship between the two. So I'm looking for a linear map that basically goes from M3 over to M3. How many constants do you guys think it's going to take to go from M3 over to M3? What do you guys think? You got 9? I heard 9. Who thinks 9? It's too easy. I'm sorry. That's a good guess. Remember when we had these exam questions where we went from, let's say, M2 to R whatever? What we do is we take the M and we square it, and then we times it by the second one. So if we're going from M3, that's M3 squared, which is 9, to M3, 3 squared, which is 9. 9 times 9, we have 81 constants. It's going to start looking really gross. And it's easy to see because if I were to write this out, if I want sigma 1, 1, so just this first component right here, and it's a function of all of my strain components, it's going to look as follows, where sigma 1, 1 is C1111 times epsilon 1, 1, C1122 times epsilon 2, 2, etc. So every single one of these stress components has 9 constants related to strain. 9 constants for just one stress component. So this is going to look pretty gross. If I were to take this and apply it to every single stress component and then write it in matrix form, we're going to get the following. So this right here would be my relationship between stresses and strains. And this right here is a 4th order tensor. That's why it has 4 indices. You guys are saying, Clayton, why does it have 4 indices? Because even though I expressed it as a matrix, it's actually a 4th order tensor. But again, you guys just need to know, or you guys just need to treat this as a matrix, which is nice for us. So any questions so far? 81 constants. Yes?
I still don't really understand why you need 81 constants if a 3x3 matrix can transform another 3x3 matrix here.
It's because if I want one component, let's say I'm just looking for sigma 1, 1, just one component. I need to take into account every single strain component. What I'm assuming right now in the most general case is that my stress in the 1, 1 direction is a function of every single strain component. So for just one sigma 1, 1, I need 9 constants because there's 9 different strain components. So this is a great question. So if I wanted sigma 1, 2, it's going to be the identical equation, 9 different constants. And it's just going to keep going for all 9 of these. So if I were to take 9 parameters, and each one is a function of 9 constants, 9 times 9 is 81. It gets really messy. But this is a great question because I just said, this is the general case. I said sigma 1, 1 is a function of every single one of these strain components. What do you guys think? Do you think that sigma 1, 1 is actually a function of every single one of these strain components? The answer is no. So this right here is our worst case. 81 constants, but we're never going to use it. We're going to start simplifying it. And as we're going to see, there's going to be 3 major simplifications that we make. Now, before we do that, I just want to call this what it is. This is called the stiffness matrix. So if I have strains and I want to go to stresses, this matrix in between here, C, is called the stiffness matrix. Now, don't get too comfortable. In structural engineering, we use stiffness matrix quite a bit. It has different meanings, but for this particular case, we would call this a stiffness matrix. And it has 81 constants. But again, we said chances are this isn't going to actually end up being 81 constants. It's going to simplify quite nice. And we can see this automatically because if I look here, I have 9 components. But is my strain symmetric? Is my strain tensor symmetric in this course? Yes. So although I have 9 components, really I have 6. So this is where all the simplifications start to happen. This is the most general form. And this was absolutely terrible to write in PowerPoint. It actually crashed my computer. It was brutal. All right, so here's the first reduction. Reduction due to symmetry of the stress tensor and the strain tensor. We said we're very lucky in this course in that both our stress tensor and our strain tensor are symmetric. So before, remember, we said that we had 9 stresses and they were a function of the 9 strains. But actually, if it's symmetric, we only have 6 stresses and they're a function of 6 strains. So this is where everything starts to go. So symmetric, this means that sigma ij and sigma ji are the same, and epsilon kl is equal to epsilon lk because of the symmetry of those 2 components. So because of this, for our stress tensor, we can say that Cijkl is equal to Cijkl, and then the same thing for our strain tensor. Cijkl is equal toCijlk. So we're ended up with this. We basically went from 9 stress components as a function of 9 strain components to 6 stress components as a function of 6 strain components. So hopefully that's not too bad thus far. How many coefficients do we have in here? 36, exactly. We went from 81 to 36 because these 2 are symmetric. Now I'm going to give you guys the biggest hint. I'm almost giving you marks. I promise you this will be on the midterm because this is important. Do you think that C, our stiffness matrix, is symmetric? Who thinks it's going to be symmetric? No one? All right, a couple in the back. Who thinks it's not going to be symmetric? All right, a lot of people think it won't be. Turns out it's going to be symmetric. All right, here's the hint. And I'm going to talk about this on the next slide. It's going to be symmetric. Now, the question that I always love to throw in exams, undergrad, graduate, it's all the same, is why is C symmetric? And I guarantee that 3 of the options will be A, because our stress is symmetric, B, because our strain is symmetric, or C, because both of them are symmetric. And then I don't know why, in students' heads they're thinking, oh, that makes sense. If stress and strain are symmetric, this must be symmetric, right? Is this symmetric in this current form? No. So there's the number one hint I'm giving you guys for exams. Just because our stresses and strains are symmetric, this does not mean that C is symmetric. You'll be amazed at how many students will select C. And I promise you guys, it will be on your midterm exam. Why is C symmetric? It's not because these two are symmetric. These two being symmetric helps because it reduces from 81 to 36 constants, but it does not prove the symmetry. The symmetry of C comes from the preservation of energy. Basically, the idea that we have linear elastic materials in this course. If I were to stretch something, it is now full of potential energy, right? Potential energy. And if I were to let it go, and it's linear elastic, all of that energy that I put into it by stretching it is fully recoverable. And that's the key here. This is why C is going to be symmetric, because of preservation of energy. Now, the proof for it is going to look a little gross, so bear with me. It has to do with strain energy. So energy stored in the material when it's loaded is fully recoverable when it's unloaded. So basically, if I have a linear elastic case, I have a nice linear line, and I want to look at something called the strain energy. The strain energy is going to be the area under this curve when it's loaded. So this is that uppercase U with a bar. Don't worry about strain energy too much. It's something I'm showing you guys for the derivation, but it's a whole topic that we're going to cover later on, because strain energy is one of the keys to all of our approximation methods. So again, just know what it is, but I'm not going to test you guys on strain energy in midterm number 2. This is just for the purpose of this proof. So this right here is strain energy. Now, if I have a linear elastic material, so linear, and it's elastic, and I have a triangle, what is the area of this curve going to be? What is the area under this curve going to be if this is a triangle? Yes, base times height over 2, exactly. So my strain energy is simply going to be 1/2 of the base, which is epsilon, times the height, which is sigma. Does that scare anybody yet? No, because this is as complex as it's going to get. So if I were to say, okay, this is my strain energy. Now, in the previous slide, I said that we can relate stresses to strains using a stiffness matrix. Basically, stress is equal to C times epsilon, right? Right from the last slide. So I can substitute that into my equation here. So instead of sigma, I got C times epsilon. So I get my strain energy is 1/2 of C times epsilon squared. You're saying, Clayton, why are you doing this? Well, it's going to become apparent a little bit later. So what I'm going to do now is I'm going to take my strain energy and I'm going to take the derivative with respect to epsilon. Again, it's not really apparent what I'm doing, but it will be soon. So if I were to take the derivative with respect to epsilon, 1/2 of C epsilon squared, well, the 2 comes down, cancels. I'm left with just C times epsilon. What is C times epsilon? Stress, exactly. This right here is equal to stress. So the only reason why I did this right here is to show you guys that my derivative of my potential, or my strain energy with respect to epsilon is just going to be equal to stress. The actual proof is down here. Cijk is the partial derivative of sigma ij with respect to epsilon kl. This is just a fancy way of saying that my relationship between stress and strain is just going to be the slope of this curve. Makes sense. Think about steel when you guys did 270, when you pulled it, you found the Young's modulus. What was the Young's modulus? Well, it's just the slope of the stress strain curve. This is just it in more of a mathematical format. Now, the reason why I did this over here, sigma ij is equal to the partial derivative of strain energy with respect to epsilon ij, is because I can take this here and I can now substitute it into here. That's the key. So now I get that the partial derivative with respect to epsilon kl of the partial derivative is equal to this. So it's the second derivative of my strain energy with respect to epsilon ij and with respect to epsilon kl. This is where the proof of the symmetry comes in here. As we can see here, all I'm basically doing is differentiating u twice. So forget about epsilon, these two right here. Just pretend that I have a function and I want to differentiate it with respect to x, and I want to differentiate it with respect to y. I want to differentiate a function twice. Doesn't matter if I differentiate with respect to x and then go to y, or if I go from y and then go to x. Doesn't matter. It's a simple function. So in this particular case, this is a simple function. So if I wanted to, instead of going partial derivative of ij and then kl, I can go from kl to ij. It's going to be the exact same thing. But notice what we just proved. Cijkl is equal to ckLij. This is where the proof of the stress tensor, or the stiffness matrix, comes into play. So if you guys ever have an exam where it says, why is our stiffness matrix symmetric? Preservation of energy. It's not because the stress and the strain tensor are symmetric. It's because of the preservation of energy, right? So that's not too bad so far. It's symmetric. Now, this is nice because if we were to take this identity and bring it back to our constants, we can go from 36 constants now down to 21, because we know that this bottom half here is going to be symmetric of the top half. It's a result of linear elasticity, or basically the preservation of energy. Now, question for you guys, linear elasticity, very realistic? If I was to design a concrete beam, linear elastic, very realistic? Who thinks yes? Who thinks no? Well, the answer is going to be no, because once it starts cracking, everything starts to change. But in reality, what we do is we treat things as linear elastic as they go. Remember, when I said that if I want to treat a nonlinear branch, I don't actually have a nonlinear function. I pick points, and I would assume linear portions. Is this valid for those linear portions? Yes. So this is what we do to simplify things, but that's outside of the scope of this course. So all you guys need to know is we went from 36 down to 21. Now, who wants to deal with 21 constants? No one. How many constants do you guys want to deal with? One constant? That's pretty amazing. Just think, if I can simulate this entire podium, if it's linear elastic with just one constant, wouldn't that be nice? You're close. How many constants do you think it's actually going to take to model an isotropic material? Those who were in the seminar are not allowed to answer. 3? I heard 3. 9? 2. 2 constants. Isn't that crazy? For a linear elastic isotropic material, 2 constants. What do you think one of them is going to be? What do you think one of them is going to be? What is the slope of my stress strain curve? Young's modulus, the elastic modulus. That's going to be one of them. The second one, as we're going to see, is the Poisson's ratio. 2 constants. But how do we get to those 2 constants? So we have to keep chugging on. So the final reduction is going to be based on planes of symmetry. And in this course, we're going to look at 3 particular types. 3. The first one is an orthotropic material. So this is a material that has a different response in all three of the basis vectors. If I were to pull along E1, that's going to be a different response if I were to pull along E2, which is also going to be different than if I were to pull along E3. Again, common example would be wood. The second one is transversely isotropic. So this is one, for our purposes, has the same response in two basis vectors, but a different in a third. So let's say if I were to have the podium here, and I were to push in the E1 direction, that will be the exact same as E2, but when I pull it in the E3 direction, so upwards, that's where it'll be different. And then finally, the last one is isotropic, where it doesn't matter which way I load it, the response will always be the exact same. So let's look at what planes of symmetry are. So in the constitutive law governing a material, it basically says it remains the same after reflection about a plane. That plane would be referred to as a plane of symmetry. So if I were to have a material right here, and its constitutive law was sigma ij is equal to c ijkl, epsilon kl, and I were to then say that this is a plane of symmetry, so it's kind of into the page, that would basically say that if I had this scenario where I reflected E1, these two, or the C's in these two cases, are exactly the same. Now, I warned you guys at the very beginning, the very, very beginning. I said for this class, matrix, tensor, same thing, same operations. This is the one time where it doesn't follow that, because again, C is a fourth order tensor. That's one thing I want to clear right away. If I want to reflect this tensor, it's not just as simple as multiplying it by Q. Remember, that's basically all we did, is we went Q times U, or Q times sigma times Q transpose. All of those rules go away when we deal with these fourth order tensors. So if C ijkl here is the same as C prime ijkl, we would say that this is actually a plane of symmetry. Now we said for orthotropic materials, they're going to have three planes, one along each basis vector, and we can see that in the next slide. So this is going to reduce our coefficients pretty drastically. How do we do that? Well, we are just going to reflect them. Once we reflect things, things start to cancel out, they become zero. But how exactly do we do that? Well, the behavior is different along three different basis vectors. Therefore, the constitutive law must be the same after the following reflections. So this is a reflection about x, this is a reflection about y, and this is a reflection about z. So again, orthotropic materials, three different directions. I can reflect it three different times. Now, the formula for reflecting a fourth order tensor is as follows. Now, I wrote it nice in Einstein notation, as we call it, but there's actually summations here from 1 to 3 all over the place. This is where, again, I just want to clarify, it's like this because this is a fourth order tensor. It's not a second order matrix. You guys don't need to know this, however. What you guys do need to know is that this is what you guys will end up with. After saying that we have these three planes of symmetry, this is our new stiffness matrix. It's pretty nice. Now, it features some things which are actually quite useful to know. The first one is this, shear decoupling. Shear decoupling. What do you guys think that means? It's basically all these zeros right here, and then all these zeros right here. What does this imply if I'm looking at stresses and strains? What do you guys think? It's actually quite a big one, quite a special phenomenon. Let's look at it. Let's say I wanted sigma 1, 1. Is 1, 1 a normal or a shear stress? Normal, it's 1, 1. If I were to calculate it using this tensor, I have a constant times epsilon 1, 1. Is epsilon 1, 1 a normal or a shear strain? Normal. And then it's going to be a constant times epsilon 2, 2. Epsilon 2, 2, normal or shear? Normal. Then it's a constant times epsilon through 3. Epsilon through 3? Normal. And then 0 times my shear strain. 0 times my shear strain. 0 times my shear strain. This is what it means. If I want a normal stress, any one of these three, they are just a function of normal strains. Just a function of normal strains. What does this mean physically? Well, if I had a rectangle and all I did was pull it uniaxially, do you expect the rectangle to start distorting? No. It should just be pulled and it'll shrink a little bit, but it's still going to remain a rectangle. It'd be pretty funny if you guys did a steel test and it somehow sheared. That's all we're saying, is that they are actually decoupled. And the same is true for the other ones. If I wanted shear stresses, I have all these zeros, so my shear stresses are not a function of my normal strains. That's what shear decoupling is. Normal stresses, just a function of normal strains. Shear stresses are just a function of shear strains. The other one is this. Look at sigma 1, 2. 0, 0, 0, 0, 0. If I were to look at the formula for sigma 1, 2, it's going to be a constant times epsilon 1, 2. So my shear stresses in a particular direction are only going to be a function of the strains in the same direction. If I want sigma 1, 2, it's going to be a function of epsilon 1, 2, and that's it. If I wanted, let's say, sigma 2, 3, it's going to be a function of epsilon 2, 3, and that's it. So there's kind of some very nice things that we're having. And this right here lays the formwork for all of our equations that we're going to have moving forward. So I said for an isotropic material, we're going to have two constants. That's for the simplest case. Isotropic, remember, it doesn't matter which way we load it. For an orthotropic material, we have 9. Someone said 9 when I asked how many, and they were correct in that this right here, for an orthotropic material, it's going to turn into 9 constants. Now, as we can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, because due to symmetry, these 3 over here are going to be the same as those 3 up here. Well, what are these constants? What is C1111? Yeah, no one knows. It has no meaning to us yet. So now we're going to define what exactly these constants are. Shear decoupling, as I talked about. So for an orthotropic material, and this is all you guys need to take away from today's lecture. What is the law of it for an orthotropic material? Well, it's going to be the following 6 by 6 matrix. All I did was I took all of those constants, C111, C1112, etc., and I switched them to actual engineering constants. So we have E, and we have nu, and we have G. Now, for an orthotropic material, remember, the behavior is different depending on which basis vector I load it. So this means that if I were to load it in, say, 1, 1, say this direction, it's going to have a specific Young's modulus. If I were to load it in 3, 3, so then vertically, it's going to have a different Young's modulus. So this is why it's 9 constants. It's 3 letters, nu, E, and G, but it depends on which direction. So the Young's modulus is the ratio of uniaxial stress to uniaxial strain in the direction of basis vector EI. The Poisson's ratio is the ratio between the axial strain in the direction EJ to the axial strain in the direction EI when the material is uniaxially stretched and along the direction of EI. Now this is going to be important for orthotropic materials because the sneakiest question, and it's on the quiz, I'm not going to cover it in class, but if you guys want an example, it's in my quiz solution video, is this. When I look at these engineering constants, does it matter about the basis vectors? Are they dependent on the basis vectors? When I look at the definitions, it talks about the basis vectors. So does the orientation of the basis vectors matter? Yes. Yes, it does. So in the example that's posted online, we give you this. We give you the stiffness matrix. But when I talk about loading the specimen, I don't load it along the basis vectors. I load it diagonally. If I load it diagonally, are these stresses the same contributing to this stiffness matrix? No. So this is where it starts to get really tricky. If I have a situation where I have this stiffness matrix, again, it's a function of the basis vectors, the stresses that I input must also be relative to the basis vectors. If they're not relative to the basis vectors, you have to rotate them first and then apply them. It's one of those very tricky things. But this, again, only is for orthotropic or transversely isotropic materials. Do you think that this is going to be the case for isotropic materials? What do you guys think? For isotropic materials, does it really matter where my load is compared to the basis vectors? Who thinks yes? Who thinks yes? Of course it does, Clayton. Who thinks no? No, it does not. Exactly, it doesn't. Because remember, for isotropic materials, it doesn't matter where I load it, the response is the same everywhere. So this is only a trick for these orthotropic materials. Now the last one down here, G, this is our shear modulus, and this is the ratio of sigma ij to the engineering strain, which is gamma ij, in the plane defined by EI and EJ. This did not convert over well in PowerPoint. This goes to one of the questions that I really specified in the lab, or I guess the seminar. When you guys have these, typically in a question, I'm going to give you everything. Very rarely will I ask for you guys to solve for something in there because it's really difficult. So typically you guys will have everything. The only thing that you have to do as a student is just input it correctly and get your strains. The one mistake I see students make is this. When we look at our shear strains, it's always 2. Always 2. And the reason why is because we are using engineering shear strains, which is equal to 2 times epsilon ij. That's the only real mistake I see students make. You guys are wondering why? Well, it's because we're defining them as engineering shear strains. So again, just note that shear strains have a 2. Do shear stresses have a 2? No. It's just these shear strains that have 2. Usually when you calculate this way, it doesn't matter, but there are some scenarios where instead of giving you stresses, I give you strains. And when you guys input this into what we call a strain vector, you guys have to multiply them by 2. That's kind of the key here. So now I just did something. I swapped it on you guys. How many of you guys noticed? Before, we had stress is equal to something times strain. But now we have strain is equal to something times stress. Is this a stiffness matrix? No. Stiffness matrix is when stress is what we're calculating. If this is the case, this is called our compliance matrix, which we call D. Now, are the stiffness matrix and compliance matrix related? Of course, they're just the inverse. Once I know this in here, and let's say I wanted to find stresses, well, I can just inverse this to the other side. So it's not too bad at all. Last thing to keep in mind is that, of course, we have symmetry. So what typically happens is I can give you nu21 and e22, but I won't give you nu12 and e11. That's when I get all the students. Clayton, I don't have enough information. Well, if you guys know this value, then you guys also know this value down here. Something to keep in mind, it's symmetric. So let's say I gave you nu21, e22, and e11. Could you guys technically solve for nu12? Yes. So when it comes to solving components inside of the compliance matrix, it would just be something like that. It wouldn't be anything crazier than that. So how's this sitting so far? I know this is a lot to take in. When you guys look at this, you're thinking, this is going to suck putting into Mathematica. That's why I said for each one of the 3 cases, orthotropic, transversely isotropic, and isotropic, write it out once, save it somewhere, so when you guys do it later, you can just recall it. Yes?
Sorry, did you say that the basis vector orientation pattern is very
It does, in a way, yes. And we're going to talk about that on the next slide. On the next slide, yeah. So this is going to be orthotropic. Any questions with orthotropic? Yes?
Can you explain why it's symmetric?
Why it's symmetric is the preservation of energy. Yeah. Basically what it means is, let's say that I have this cable and I fix it at that end. and it's steel, so the response is the same. It's fixed at that end. If I were to pull it, I'm going to get a response. All right? Now, let's say I fix it at this end, but then I pull it this way. Should the response be the same? That's the preservation of energy. It doesn't matter which way. It should be the exact same. Great question. Again, why is it symmetric? Preservation of energy. It will be on the midterm. I promise you guys that. So an easy 4% if you guys remember. So that's orthotropic. Now, transversely isotropic, it's a case that you guys very rarely see because it can be very hard. If I were to give you a question that was kind of mentioned here, where I give you an orientation that is not aligned with the basis vectors. You will have to rotate in some cases, but since it's the same in two planes, it actually becomes a little bit more difficult to see how that rotation goes. So it does matter, I will tell you that, but I would never test you on it like that. If I were to test you guys on transversely isotropic, I would make sure that everything is aligned correctly, so you guys can just use the formula. You guys wouldn't have to rotate it. That's too mean. Even for orthotropic, I guess I'll say it now, I wouldn't ever give you guys something you have to rotate. It's something to look at in the quiz because it's kind of interesting to note, but that's just too mean. Like that would take you guys, I don't know, 15 minutes to code. And if it's an hour and 20 minutes, I guess an hour and 20 minutes, yeah, 80 minutes, 80-minute exam, that's just too much for one question. I would never do that to you guys. If I give you an orthotropic material or transversely isotropic, everything will be aligned. I'm not gonna try and get you guys with that. That's too mean. Okay? I don't want you guys to hate me that much. All right, so for a transversely isotropic linear elastic material, there's a plane in which every plane perpendicular to that plane is a plane of symmetry. Basically, what this means for you is the behavior is the same along two basis vectors. We already had this diagram before, and what I can say is, okay, all of these are planes of symmetry. And as you can see, all of the planes of symmetry actually go about an axis. So we call this the axis of isotropy right here. Because even though I have them perpendicular, if I were to have a plane that, let's say, goes at an angle like this, well, that's also a plane of symmetry. Same if I had a plane that goes like this. So for this case, this would be your compliance matrix over here. It went down from 9 constants down to 5. So now we only have 5 material constants. Everything's starting to look better. And again, always remember that these are going to be symmetric. Always remember that. It's a fun trick in exams. All right, the last one, which is the one you guys are going to see almost all the time, isotropic linear elastic material. Now, for this case, isotropic, everything is the same, or the response is the same, no matter what coordinate system. So again, I can load it whatever way I want, the response is going to be the same, and that gives us this right here. So as we can see, 2 constants. What are my 2 constants? Young's modulus E, Poisson's ratio, right? 2 constants. What is G? Shear modulus. But isn't that a 3rd constant? Are you saying I'm wrong? So this is where it gets fun. It's 2 constants because the shear modulus G is actually a function of nu and E. So if I give you Poisson's ratio and I give you the Young's modulus, you can calculate the shear modulus. So that's why it's actually 2 constants. I know it's tricky. Sorry to scare you. So it's reduced to 2 material constants. The Young's modulus, which is the slope of the stress strain curve during a uniaxial tension test. You guys have done a million of those. And the Young's modulus, which is the negative ratio of the transverse strain to the axial strain in a tension test. Now, I didn't talk about the Poisson's ratio too much because I wanted to save it for this slide. I wanted to keep it in a simple case. What is Poisson's ratio? What does that account for? Do you guys remember? Who remembers what the Poisson's ratio accounts for? It accounts for this. If I were to take a square and I were to compress it, of course it's going to start deflecting downwards. I'm putting stress on it. But what happens in the lateral direction if I were to compress it downwards? It's going to expand. That's what the Poisson's ratio is. Basically, it's a ratio of the transverse strain. So how much strain, when I push downwards, how much strain is it going to have horizontally to the axial strain? So it's a ratio of how much strain I'm actually pressing compared to how much it expands. And then, of course, if I were to compress it, expanding or contracting? Contracting. Would my strain be negative or positive? Negative. If this was expanding, what would my strain be? So if I were to just take the ratio, would I get a negative or a positive number? Negative. Because one's going outwards, one's going the other way. So that's why we take that ratio and then we times it by a negative to give us a positive number. That's all we're doing. Now, something we're going to talk about kind of in the next lecture. So on Tuesday, we're actually going to start going into these parameters a little bit more. Do you think that there's materials that when I press downwards, it also contracts? Yep, exactly. It's one of those funny things that research over the last few years is proving a lot of, not proving, I don't want to say that, but it's showing that the math has some faults. As we're going to see, our Poisson ratios have to be mathematically between -1 and 0.5 for it to be stable. But we can see that there's materials with a Poisson ratio of like -10, like just crazy Poisson ratios. What does it mean? Well, mathematically it means it's unstable. And if you look at the materials, most of them are. One of them would be foam. You guys know that spray foam crap? That would be one of them. And you think about it, it makes sense. If I were to just shoot some spray foam, once it reacts, it goes crazy. But that's not really stable. You don't want your building to start expanding like that. You'd be in for a bad time. So that's the Poisson's ratio in a nutshell. I already hinted at what about G? Well, the shear modulus G is simply going to be E divided by 2 multiplied by 1 plus B. Another material constant that we have is the bulk modulus. Now the bulk modulus is the slope of the hydrostatic stress versus volumetric strain of a linear elastic material. So it can be defined as follows. Very rarely will I ask you for bulk modulus because it doesn't appear in any of the equations. What does the bulk modulus do for us? What do you guys think? Does anyone know what the bulk modulus is used for? Exactly, no one knows. Who cares? This is generally used to find the stiffness of an object. The stiffness. How much stress is it going to take to start deforming something? So if I want a really stiff object, I can look at the bulk modulus to try and figure out what that is. What do you think is stiffer? Steel or concrete? Steel or concrete? Concrete. By a lot? Maybe. The answer is steel. Steel is 8 times stiffer than concrete, approximately. What's the Young's modulus of steel? 200,000. Young's modulus of concrete is around 30,000. 30,000. Isn't that crazy? Here's where it gets fun. When I define the stiffness of a structure, it's the Young's modulus E times the moment of inertia I. 2 factors. One related to material, one related to geometry. When I build a very, very tall building, I want it to be stiff because you guys know that if I have a cantilever beam, the moments at the top, or the force at the top is going to create a lot of moment. So if I have a really tall skyscraper, there's going to be a lot of moment. I need it to be stiff so my building's not doing this in the wind. For those kind of structures, we use concrete. Concrete. But why? Steel is much stiffer. So why do we use concrete? The geometry. When you guys see a steel beam, I can go hug it. I can go wrap my arms. That's a nice steel beam. Can you guys go wrap yourselves around this big concrete wall? No. So that's why we use concrete, because we can get that stiffness by just making it massive. The reason why we do that is because it's cheaper. It's cheaper. It's easier to pour all that concrete than it is to Buy steel. Steel's expensive. So that's another thing. When you start designing things, you have to start taking into account economics. Anything you guys can imagine can be designed. Believe me, anything you guys can put your minds to, no problem. How much money it's costing, that's where it starts to limit you guys. So you guys are going to find yourselves in that predicament a lot as a structural engineer. All right, so the last thing we're going to talk about is plane stress and plane strain. So those laws that we just talked about, they're for 3 dimensions, right? 3 dimensions. What typically happens, though, is if I want to simulate something in 3 dimensions, it's going to take a lot of computation time, a lot. So one of the things that we do is we simulate things in 2 dimensions, 2 dimensions. And when you do that, you either have to specify plane stress or plane strain. It's going to be one of those 2 things. So the first one is plane stress. Now this is a scenario where all the stresses in a material act in the same plane. So sigma 1, 3, 2, 3, and 3, 3 are going to be 0. Basically, if this table surface was my plane, all my stresses act in this plane. I'm not going to have a stress coming out of the table. It's all going to act in the exact same plane. So if this is the case, my stress tensor has a bunch of zeros. So therefore, I can find specific strain values. And this is going to be the law between them. So as we can see, it's nice. And this is where we save a lot of that computation time. We don't need a 6x6 matrix. We only need a 3x3. Now, here's the only thing you guys have to know when it comes to plane stress. Is there an epsilon 3,3? The answer is yes. There is an epsilon 3,3. But does this calculate epsilon 3,3? No. So when you guys deal with plane stress, there is epsilon 3,3, but you guys can use a separate formula to calculate it. Basically, what we're saying in this plane is if I'm assuming plane stress, my material into the page is freely allowed to expand or contract. That's it. If I just let something expand, will there be stresses? I'm not restricting it. No, exactly. There's going to be no stresses. Think of the concrete sidewalks. You know how we have that little gap for expansion and contraction? Well, due to the weather, it expands. So there's going to be strain because it's expanding, but there's no stresses. It's one of those kind of scenarios. So this is what we have. Plane strain, on the other hand, is the opposite. It's assumed when all the strains in the material act in the same plane. So epsilon 1, 3, 2, 3, and 3, 3 are 0. So I get my strain tensor, my stress tensor, and it's going to be similar format where we have a nice relationship between the 2. Now in this case, do I have sigma 3,3? Yes. Over here, but does it calculate sigma 3,3? No. So what we have to do is we have to calculate sigma 3,3 manually. Now again, when I said plane stress, I said it's allowed to freely expand or contract in that direction. If I'm limiting the strain to 0 in that direction, can it expand or contract? No. And because of that, there has to be stresses to ensure that it doesn't expand or contract. That is what sigma 3,3 is. It's the stress making sure that my material doesn't expand or contract, make sure that it stays the way that it is. So those are going to be the constitutive laws. Long lecture, long theory lecture. But basically, you guys just need to know 5 things. The compliance matrix for orthotropic, transversely isotropic, and isotropic materials, plane stress, and plane strain. Those who took the seminar on Tuesday said, well, actually, I'm not sure what they said, but basically the assignment this week is easy. It's just substituting values in and calculating. That's it. The only thing that people don't like about this week is when you're defining these in Mathematica, well, this one's not bad, but most of them, they get pretty ugly. So that's the only real drawback. It's easy because there's no tricks. It's just straight calculations. The thing that sucks is that you guys are going to have to program it in Mathematica. But again, once you have it once, you can do it again and again and again. So is there any questions about constitutive laws? Everybody's happy? Perfect. I don't like giving this lecture. It's too much. It's a lot of material to digest. All right, so we're going to go into some examples now. This is when I started typing them out, so it's looking fancy. So again, I promise you guys, Clayton guarantee right here, I will throw this question on a midterm. on the midterm. Midterm 2, this is going to be on it, I promise you. It says in the linear elastic structure, the matrix of coefficients relating the stresses to the strains is symmetric because of A, our stress tensor is symmetric, B, our strain tensor is symmetric. Well, I guess I flipped them. C, both the strain and the stress tensor are symmetric. Or D, the strain energy inside the body is independent of deformation, or the path of deformation. So what is the answer? Who thinks D? Almost everybody, it's D. This is basically saying preservation of energy. Again, a lot of students say, oh wait, if this is symmetric, oops, I guess I turned this off. If this is symmetric, well, it must be because of some other symmetry. No, because of preservation of energy. Again, I promise you it'll be on midterm. It's something very important for us. So that's the only multiple choice. Let's get into an actual fun question. A linear elastic material has a Young's modulus of 1,000 MPa. Let's talk about that. 1,000 MPa. Is that very stiff? Yes or no? What is steel? 200,000. Exactly. So that's not a lot. And a Poisson's ratio of 0.2. What do you think? 0.2 pretty realistic? Yeah? Yeah, it's pretty realistic. Concrete's around 0.2. Steel's around 0.3. So yeah, pretty realistic. If the stress changes from sigma 1 to sigma 2, so as we can see, we have two different stress states. What is the total change in strain energy stored in the material due to deformation associated with the change in stress? Ooh, strain energy. Who remembers what strain energy is? Who remembers what strain energy is? It won't be on your midterm, I promise you guys that. So we're going to talk about it after the midterm. But I talked about it in the slides today. Who remembers what strain energy is? Exactly. Area under the stress strain curve. So if I were to come down here, say, okay, I have a nice curve. It's going to look something like this. We know that we have stress. We have strain. What would my function look like if it's linear elastic? Straight line. Linear and elastic, we're going to have a straight line. So I'm just going to go to my dots. Where are they? Something like this. So if I wanted the area under this curve, what's my function going to be? So if this is u, it's going to be equal to, what's going to be equal to? What's the area of a triangle? Exactly. 1 over 2 base, in this case, it's strain, times sigma. Now, is this for the uniaxial case? Yes. Are my stress states uniaxial? No. So what do you think my strain energy for a triaxial stress state is going to be? What do you guys think? It's actually kind of a trick question. It's just going to be that formula just for every single direction. That's it, and then added together. So if I were to go U total, it's going to be 1/2 of sigma 1,1 times epsilon 1,1 plus 1/2 of sigma 2,2 times epsilon 2,2, and then everything else, of course. But I'm not going to add the rest because the rest are zeros. We only have sigma 1,1 and 2,2. So now we have this, and we're saying, okay, we're on the right track. We want to find basically the strain energy in both of these scenarios and then just find the difference. We need sigma 1,1, sigma 2,2. I got those. What's my problem? What don't I know? Strain. So this is why we have to use our constitutive laws. So I'm going to switch back to pink. It's a little bit easier to see. And I'm going to zoom out. Actually, I'm not going to zoom out. I'm going to come down here. If you guys look at your slides, you guys have this exact formula. And I didn't want to write it out. This would be 5 minutes of you guys watching my forehead. This is what we have. So can we find our strains? Yes or no? Are we missing anything? Are we missing anything? We're given Young's modulus. We're given nu, the Poisson's ratio. Are we good to go? Yeah, we just have to calculate everything. Now, what's nice for us is what is sigma 3,3? 0. Get rid of that. What is sigma 1,2? 0. Sigma 1,3? Sigma 2,3? 0. So we know from our stress state that we only ever have sigma 1,1 and 2,2. The rest are equal to 0. So all we have to do is go down and basically multiply everything out. So I'm going to come down here. Actually, I'm going to copy this, save some time. Is that the copy button? All right, let's see. Copy. Oh, look at that. Perfect. So all you guys have to basically do is go through this matrix. If we're looking for epsilon 1, 1, all we're going to do is multiply this row. Oh, I was hoping that would straighten out. Multiply this row by this vector. So as we can see, there's actually only going to be two components because we have so many zeros. It's going to be this factor times sigma 1, 1, this factor times sigma 2, 2, this times 0, 0, 0, 0, 0. So it's basically just going to be those two. So I'm going to come down and say, okay, I got 1 over e times sigma 1, 1. So we have 1 over e, and we have sigma 1, 1. I come up here. I guess actually this can kind of do both. Then I go negative nu over e times sigma 2, 2. So if I keep the 1 over e kind of factored out, I get this right here. Negative v sigma 2, 2. And the rest, of course, are going to be zeros. Is everyone comfortable with where I got this from here? Everyone comfortable? Hoping so? All right, perfect. So that's going to be our first component. So now, oops, this is going to start erasing stuff. If I want epsilon 2, 2, it's going to be the second row multiplied again by this column. So we got 1 over e as kind of a factor on everything. So I'm going to keep this out, 1 over e. I look up at the first one. The first one times sigma 1, 1 is negative nu over e. I already took out the 1 over e, so negative nu sigma 1, 1. And then plus, we're going to scroll up. Oops. And then 1 over e times sigma 2, 2. 1 over e times sigma 2, 2 is just going to be sigma 2, 2. Now here's a fun question. I just loaded along sigma 1, 1 and sigma 2, 2. That's it. Is there going to be epsilon 3, 3 component? Is there going to be an epsilon 3, 3 component? Who thinks no? I didn't load in 3, 3 direction. So who thinks there will be? You guys are too smart. There is going to be. And you guys can see that because if you were to look at this formula, we can see that once we multiply it out, we get something like this. So I'll just go down. We have 1 over e. And then we have negative sigma 1, 1, or I guess negative nu times sigma 1, 1 minus nu sigma 2, 2. What about shear strains? Am I going to have any shear strains? No. Remember that concept of shear decoupling. My shear strains are only going to be dependent on my shear stresses and vice versa. Since I don't have any shear stresses, I'm not going to have any shear strains. So I'm just going to erase this. We're going to go down. We're going to say, okay, well, we know the last three components, of course, are 0, 0, and 0. So now I have all of my strains as a function of stresses. So if I go back to my formula, actually, I'll just copy and paste it and bring it down. Copy. all I have to do is substitute everything in to make it a function of sigma 1, 1 and 2, 2. So, oops, I want to go back to marker. So u is going to be equal to 1/2 sigma 1, 1 is just sigma 1, 1. Epsilon 1, 1, we now have a formula for. It's 1 over e multiplied by sigma 1, 1 minus nu sigma 2, 2. And that's going to be for the first one. Then I go to the second one. I already factored out the 1/2. So this is going to be plus sigma 2, 2 multiplied by 1 over e multiplied by negative nu sigma 1, 1 plus sigma 2, 2. So as we can see, it's getting pretty ugly. But if we look here, what is this a function of? Sigma 1, 1. Do we know that? E. Do we know E? Sigma 1, 1, 2, 2. Do we know them? Yep. Poisson's ratio? Yep. We know absolutely everything in this equation. So for this question, we just finish it off by substituting everything in under the two states. So I'm going to say U1 for sigma 1, 1 and sigma 2, 2 are both 10. This actually, let me just simplify it. This actually simplifies really nicely to 1 over 2e sigma 1, 1 squared plus sigma 2, 2 squared minus nu sigma 1, 1 sigma 2, 2. You guys can do this simplification if you want. Mathematica does it for you, which is even better. So if I were to calculate things, U1, well, we have 2 times E. We know E is 1,000. We have 1 on top. Sigma 1, 1, we said was 10 squared plus sigma 2, 2, also 10 squared minus nu 0.2 times sigma 1, 1, 2, 2, so 10 times 10. And if you guys were to do that in your calculator, you get 0.08. So it's just plugging and chugging your way through the rest of the question. If I were to come down here and say, okay, well, that was for 1. If I were to look at my second state, U2, and I were to go up, just to show you guys, the only difference now is instead of 10 and 10, we now have 20 and 10. So sigma 1, 1 is now 20. That's the only difference, if you guys will. So we come down here. It's still going to be 2 multiplied by 1,000 over 1. Sigma 1, 1 now is 20. So 20 squared plus sigma 2, 2, same thing, 10 minus 0.2 times 20 times 10. And if you guys throw that in, you get 0.21. So since we have U1 and U2, the change is just going to be U2 minus U1, which is equal to 0.13. Really boring stuff, as you guys are seeing. How do you guys feel? Boring, yes. You guys don't have to tell me it's boring. Trust me, I know it's boring. But is it hard? No, it's just a bunch of substitution over and over again using a 6x6 matrix, and that's it. Once that's done, you guys get your answer, you're good to go. On the midterm, you have Mathematica. You guys will have all of those matrices stored, ready to go. Just type in the inputs, really. So that's it. Hopefully not too bad. So that's strain energy. There's a second question. The figure represents a specimen under a confined compression test. The vertical stress is negative P, where P is a positive real number, while the confining pressure is equal to negative 3P. If E is the Young's modulus and D is the Poisson's ratio of the specimen, what is the volumetric strain? You guys remember what volumetric strain was? Who remembers? It's just going to be the trace of our strain tensor. So it's going to be epsilon 1, 1 plus 2, 2 plus 3, 3. That's it. It's a representation of the kind of the normal strains acting. So epsilon 2, 2 plus epsilon 3, 3. So again, the end of this question, it wants us to find strains. We're not given strains, we're actually given stresses. So I can say, okay, well, I got my Cauchy stress tensor sigma. Really quick, referring to the picture, is there any shear strains? No, no shear strains. So if we were to look at this, we can say, okay, it's going to be negative 3p, 0, 0, 0, negative p, 0, and then 0, 0, negative 3p. The reason why I knew which one went where is because in the actual figure, it shows the axis. So the vertical axis is E2. E2 has a compression P. And then this axis, E1 and E3 coming out here, well, they're both under compression of 3P. Any question where I got my stress tensor from? No? Perfect. So all we have to do is say, okay, I have my stresses, looking for strains. I have a very nice, well, not very nice, but I have an equation for that. We said that we have no shear stresses. So we know, I'll switch this to red. We know that this is going to be 0, 0, 0. And we have values for our normal stresses. So I can kind of erase those. We have negative 3p, negative p, and negative 3p, just like that. So then it's just a matter of going through everything. And I guess we can just find it. I won't do an actual vector. Epsilon 1, 1. Well, that's going to be equal to 1 over e times negative 3p times negative mu over e times negative p times, or I guess plus negative mu over e times negative 3p. Again, it just gets really, really boring. So we go over here, it actually simplifies a little bit to 1 over e multiplied by negative 3p plus 4 nu p. Epsilon 2, 2. If you guys were to do all the calculations, it's going to be 1 over e multiplied by negative p plus 6 nu p. And then epsilon 3, 3. Negative 3p. It's the same as above. So all you guys have to do is just add them all together. And you guys get that the volumetric strain, again, it's just all of them together. 7p over e, 2 nu minus 1. Again, really boring. I hate having to give you guys these because it puts me to sleep just writing it. I can imagine how you're feeling right now. But all I want you guys to take away is this. Again, calculations are easy. If this was Mathematica, all you guys would have done is just put in your stress tensor and then find your strains and add them together. Takes you, what, 20 seconds? Yes. The shape? Yep. That's a great question. So what happens is it's had an axis system. Actually, let me just draw the axis system. So the axis system was kind of like this, where it was E1, E2, and E3. So for E2, it's pretty easy to see that it's being compressed by negative P. So hopefully that one's not bad. And then all along the horizontal direction, it's being confined by negative 3P. So one of those fun things that I'll tell you guys right now when it comes to exams, I will never give you a figure in 3 dimensions with shear and expect you guys to start. It's too much. If it's 3 dimensions with shear, I'll probably just give you the stress tensor. I won't actually make you guys derive it. Because that would suck. You guys do all that work that we just did, but your only mistake was messing up on the stress tensor. Ooh, you guys wouldn't be too happy with me. I want you guys to be happy. This should be fun. You guys enjoying it? Are you guys enjoying your schooling this year? It's supposed to be fun in third year because it's not so much that theoretical crap that you learn in first year, it's actual applications. You guys are doing structural design. Are you guys looking at actual scenarios? Yes. You guys are doing water. I don't know what they do, pipes. Bernoulli equation, does that actually apply? Yes. Construction, well, construction is just construction. It's more just trivial stuff. But joke's on us because they're the ones getting paid. There's 3 tiers of payment. Structural engineering, what do you think? Do you think we're the most paid or the least paid? Least paid. We're at the bottom. Building the building. You think you get paid more than the structural engineers? Construction engineers? Yes. You get paid a lot more. Basically from 70,000 to over 100,000. What's the final tier? Designing the building, building the building. Who gets paid the most? Person selling the building. You have no idea.